Hi everybody, this is our lecture on section 13.8 or 6.8, and that's on the divergence theorem. And this is the last section in the text. Okay, so let S be a closed two-sided surface. So closed meaning it's got an inside and an outside. So unlike surfaces with a boundary, there are surfaces, well, there's essentially one, and combinations thereof, of one-sided surfaces that have a boundary. The Moebius band is the prime example of that. As far as closed surfaces without boundary, there is no one-sided surface that lives in three dimensions, although in higher dimensions they do exist. Closed two-sided surface. So closed meaning no boundary. So mainly we're interested in sort of sphere-like objects. All right, so this kind of potato shape here, or other things of, more sharp geometric objects. So closed two-sided surface oriented outwardly. So this is S, and the orientation of the surface is out. So side 1 to side 2 is inside out, inside 2 out. So something like that, or, a nice example is the cube. We've talked about cubes before, but we've avoided sort of doing examples because it's sort of tedious to parameterize a cube because you have to do each side separately. So cube, sphere, things of this sort. So vaguely sphere-like things. Let E be the region inside S. Denote the solid three-dimensional region inside S. So the divergence theorem states the following. If F is a vector field, with continuous partial derivatives, inside of S, on and inside of S, then the vector flux over the surface S, so the flux of the vector field out from inside to outside, is equal to the triple integral of the interior of S, that was E, remember E is the three-dimensional region inside of S, of the divergence of F, dV. So the surface integral becomes a triple integral. The triple integral of what function? The scalar function that is the divergence of X. And remember, what was the divergence of X? So given F equal to PQR, the divergence of F is px plus qy plus rz. And what does the divergence measure? It sort of measures how much of the vector field flows out of any given point, flows outwardly from the origin, in the direction from the origin at any given point. So sort of how much energy is being created and cast outward at every different point, right? And that's kind of like what the divergence theorem is saying, that the total amount of vector flux outward from the inside of the surface to the outside of the surface is essentially the amount of energy that's created inside the surface, in the region inside the surface. So divergence of F is kind of like the amount of energy created and directed outwardly from the direction of the origin at that point. And it's interesting in a lot of different fields as well, not just in calculus, but if you ever do get a chance to take some combinatorics, in particular network theory, there's a discrete, a finite analog of the divergence theorem. So it's an interesting idea, and it comes into play in a lot of different areas of mathematics. Okay, one word of caution: make sure this notion that you've got continuous partial derivatives. It's kind of important because it does come up that, like a lot of the vector fields we've looked at, they're not continuous at the origin. Okay, so I'll throw an example like that at you in a little while. So let's just take an example to start. So we'll say that f is equal to xy, comma, z squared, comma, x squared, y squared. And let's calculate, and s is the cube. Shown here. So 0 to 1 for x, 0 to 1 for y, 0 to 1 for z. So it's just this cube whose sides have unit length. So s is the cube, again oriented outwardly. All right, so on the top surface of the cube, it's going up. On the right-hand surface, it's going to the right. On the left-hand surface, going to the left. Bottom surface going down, coming forward here, so on and so forth. Okay, look at this here. Okay, each p, q, and r, they're all just polynomials. Okay, so there's no discontinuity here going on, because polynomials, they're always continuous. So here the divergence, and let's calculate the surface integral of f dot ds. Now, if we were to do it directly, we'd have to parameterize each of the 6 faces of the cube. So to do this manually, we'd have to parameterize the 6 different faces of the cube. So for example, bottom face, the bottom face of the cube is r, x, y. X is x, y is y, z is 0. For 0 less than or equal to x less than or equal to 1, 0 less than or equal to y less than or equal to 1. The top face is r, x, y, x is x, y is y, z is 1. 0 less than or equal to x less than or equal to 1, 0 less than or equal to y less than or equal to 1. The front face, right, what's that? The front face is, well, let's say the back face. So the back face is R, so this is X, Y, Z. So the back face is R, Y, Z, which is X is 0, Y is Y, Z is Z. 0 less than or equal to Y, less than or equal to 1, 0 less than or equal to Z, less than or equal to 1. The front face is R, Y, Z. X is equal to 1, Y, Z, with the same thing here. 0 less than or equal to Y, less than or equal to 1, 0 less than or equal to Z, less than or equal to 1. And then there's the left face, right face. So I'll do that calculation later, but I'll pause the video to actually, show you that calculation. I'll write out the whole thing. But let's do it with the divergence theorem, and I think I will finish the calculation without the divergence theorem on this page. So let's calculate with the divergence theorem. So F was equal to, what was that vector field? xy z squared, x squared, y squared. So the divergence of F is equal to partial derivative of this with respect to x, that's y, plus partial derivative of z squared with respect to y, that's 0, plus the derivative of x squared, y squared with respect to z, that's 0. So it's just y, right? Another reason why this could be useful, especially when you're dealing with polynomial type vector fields. Because the divergence, when you take derivatives of polynomials, they get simpler, typically. Right? So the vector flux across the surface, which is the cube, of f dot ds is equal to, by the divergence theorem, triple integral over E inside the cube of the divergence of f, which is equal to dv, which is equal to, in our case, well, the cube was just x from 0 to 1, y from 0 to 1, and z from 0 to 1. Y, and we'll do dy, dz, dx. We'll do y first. So antiderivative with respect to y, 1/2 y squared from 0 to 1 gives you a half. And then dz, dx. So the area of what's left over is just 1, so the whole thing is a half. Just very quickly, that integral is a half. Now what I'm going to do here, I'm going to pause the video, and I'm going to fill out that whole calculation just without using the divergence theorem, calculating the surface integral on all 6 faces. Okay. So we've got that cube, right? And the orientation is outward. So the right-hand face is oriented to the right. Left-hand face oriented to the left. Top face up, bottom face down, front face forward, back face back. Right? So we parameterized all the faces. Bottom, top, back, front, left, right. Left is, just x and z are varying. X and z, x is x, z is z, y is 0. Right face, x is x, z is z, y is 1. And both of them are for x and z between 0 and 1. So, the surface integral, the flux, vector flux, f dot ds over the whole cube, right, is the sum over the same vector flux over the 6 different faces. Okay? So, for the bottom face, we take the derivatives, Rx is 1, 0, 0, Ry is 0, 1, 0. And then it's Ry cross Rx is 0, 0, negative 1 for the downward orientation. Ry cross Rx for the downward orientation, the right-hand rule, rather than Rx cross Ry for the upward orientation. Anyway, so, and then f of r of xy X is X, Y is Y, and Z is 0. Actually, that's a 0 there. X is X, Y is Y, and Z is 0. Well, it doesn't matter because this is f of r of xy. This is ry cross rx. So this integral is a double integral. The surface integral is a double integral of this dot product dA. Which turns out to be the integral from 0, 1 to 0, 1 minus x squared y squared dy dx, which is minus a ninth. For the top face, it's plus 1/9. You get the same integral because the dot product is this vector dot 0, 0, 1. So it's positive x squared y squared rather than negative x squared y squared. So it's the same answer, just the negative of it. So 1/9. Back face was 0. Front face is a half. Left face is minus a third. Right face is positive a third. So over the whole sphere, the flux across the cube, across the whole cube, is the sum of those fluxes across each side. 1/9 minus a ninth plus 0 plus a half plus a third minus a third is a half, which is, what the divergence theorem gave us just, right off the bat there. Okay? Let's do another example. Just divergence theorem. So we'll let f be equal to yxz squared. Calculate f dot ds, where s is the outward orientation of the surface between, the surface consisting of the paraboloid z equals 4 minus x squared minus y squared and the disk of radius 2 in the xy plane. Okay, so what that's going to look like, you've got the paraboloid here, right? So the surface has to be closed. So we looked at this like with Stokes' theorem, right? But with Stokes' theorem, you don't have a closed surface. So here, that's the paraboloid in the z equals 4 minus x squared minus y squared, and then here's that disk, right? So that's the surface, S, oriented outward. So outward in these directions, and then upward here right at the top. And then the disk on the bottom is oriented downward. Okay, so the inside of S right is, well, in spherical coordinates, not spherical, in cylindrical, is E equal to, well, we have the disk of radius 2 down here. So it's 0 less than or equal to little r less than or equal to 2. And then theta is from 0 to 2 pi. And then z is from 0, the xy plane, up to the paraboloid, 4 minus x squared minus y squared, which is 4 minus r squared. Right, where z is equal to 4 minus x squared plus y squared. So in polar coordinates, it's that, 4 minus r squared. All right, so again, f was equal to yx squared. So the divergence of f is equal to 0. Derivative of y with respect to x is 0. Derivative of x with respect to y is 0. Plus the derivative of derivative of z squared with respect to z is 2z. So it's just 2z. So the vector flux across that surface S is equal to, by the divergence theorem, the triple integral over E of the divergence of f dv. So that's the triple integral, right, over E of 2z dv. Now I'm going to switch to cylindrical coordinates. So I've written this in terms of Cartesian coordinates. Now we're going to switch. Well, it's always written initially in terms of the original coordinates, which are Cartesian here. So now we're going to switch to cylindrical coordinates. So that's z, and then r is 0 to 2, and theta is 0 to 2 pi. So that's 2z dz r dr d theta. All right, so you do z first, and then you multiply by r, and then you get dr d theta. So this is equal to, antiderivative with regard to z is 1/2, well no, it's just z squared, from z equals 0 to z equals 4 minus r squared. R dr d theta. So this is equal to the integral from 0 to 2, integral from 0 to 2 pi, r times 4 minus r squared squared dr d theta. Now for the antiderivative with respect to r, I could multiply it out, but actually what you can do is do a u substitution, let u equal 4 minus r squared, so du over minus 2r is dr, dr d theta, excuse me. There's the extra r. So what we get here is that this is equal to antiderivative minus 1/6, 4 minus r squared to the third, from r equals 0 to r equals 2 d theta. Make sure we got that right. So 3 times 1/6 is 1/2. 4 minus r squared squared times minus 2r, minus 2 and the 1/2 canceled gives, yeah. So that's the correct antiderivative. Evaluating at 2 and at 0, we've got, well, at 2, this is just going to be 0. And then at 0, so that negative becomes a plus because we're subtracting. So 4 to the third. 4 to the third is 64 over 6. D theta, just 32 over 3, times 2 pi. So that's equal to 32 times 2, 64 over 3 pi. Okay? So another nice example of the divergence theorem. Now we could actually calculate this surface integral directly, right, by parameterizing the paraboloid and then parameterizing the disk and calculating those two things separate, the vector flux across each surface separately, across the paraboloid from bottom to top and across the disk from top down in the downward direction. So actually I did this in my notes, but I'll just leave it out. Basically, over the paraboloid, the vector flux is this, and over the disk it's 0. So right? Because at the disk, what's z? On the disk, we have z is equal to 0, and x is x, and y is y. So the vector field and the xy plane points in the direction of the xy plane. Right? The vector field down in the xy plane is just pointing in the direction of the xy plane. So how much of that is pointing down? Nothing. The component in a vector in the xy plane, the component in the downward direction is 0. Right? So there's no vector flux going down. It's all just going across the paraboloid. All right. So here is an example where it doesn't work. So I guess a non-example. So we let f be equal to, now we did this example back in section 6.6. We calculated it directly. So it would be in here. I think it was probably the last example that we did. Yeah. So f is equal to 1 over x squared plus y squared plus z squared to the 3/2 times the vector x, y, z. So it's essentially vector v over the length of v to the third. Okay, so that vector field, that was the one that models the explosion at the origin, because the flux across any sphere, so we did the flux across the sphere of radius k, and the k is canceled out, and we just got 4 pi. So the flux across any sphere, no matter what the radius, the total flux is always the same, 4 pi in this case. Okay, so that would be the behavior, for the law of conservation of energy, that would be the behavior of like the force, concussive force made by an explosion at the origin. The total concussive force across any sphere would always be the same, no matter how big the sphere was, as long as that energy is not dissipating. Anyway, so it was 4 pi. But why I bring up this example, this won't work with the divergence theorem, because at 0, the derivative doesn't exist. There's no derivative. The function itself doesn't exist. Right? And you need continuity. So there was this v over the length, so the vector field was this, so that's 1 over x squared plus y squared plus z squared to the 3/2 times x, y, z, and s was equal to the sphere centered at the origin of any radius. Right, this f does not exist at the origin. So f does not exist at the origin, which is inside the sphere. Alright, so f does not exist at the origin, which is inside the sphere. So f does not have partial derivatives, much less continuous partial derivatives, inside the sphere. So divergence theorem doesn't apply. Unfortunately. So, that's one very interesting example of a vector field. But the flux across a sphere or any other surface inside, centered at the origin, cannot be calculated using divergence theorem. It needs to be calculated directly, which we did in section 6.6. I'd just like to give you an idea of basically how the proof for this goes, of the divergence theorem. Much the same idea as the proof for Green's theorem. For the proof of the divergence theorem. Okay, step one. So prove the divergence theorem works on a cube. A less than or equal to x, less than or equal to b, well, a1 less than or equal to x, less than or equal to a2, b1 less than or equal to y, less than or equal to b2, c1 less than or equal to z, less than or equal to c2. So prove that it works on a cube. You know, and we did the calculation over a cube, so it is a bit tedious, as you saw. But, you know, I mean, it can be proven to work over a cube. Right, and then for any step two, prove that it works over a stack of cubes. So you take your cubes and you stack them up, you know, and you make your pile of cubes, all of the same size. It's much harder to draw here in 3 dimensions. And, oh, we got some cubes back there, so on and so forth. And then step 3, right, any S can be estimated as closely as we'd like. We would like using really tiny cubes. Right? So all you guys that play Minecraft, right? I mean, everything's made out of cubes, right? Everything's made out of cubes. So you can take a sphere and make it out of cubes. And that's essentially what you get when you look at Minecraft sometimes, right? When you see something kind of round out in the distance, it's got this very cubic, pixelated kind of look to it, right? That's essentially what you're doing. You estimate in any smooth surface, you know, by really, really tiny cubes, by a stack of really tiny cubes. So you estimate the integral as closely as you would like using these stacks of cubes. That's essentially the same idea we did with Green's theorem. We proved Green's theorem worked over a square, or a rectangle, I guess it was. These are rectangular boxes too. Over a rectangle, and then worked over a stack of rectangles, and then for any simple closed curve, we estimated, you know, the inside of the curve, you know, using those rectangles. And that's so much of how calculus is done. Things are done by estimations of that sort. Okay, so that's the end of the lecture on this section. And that is all the material for the course. Congratulations, everybody.